In this sequence, we will continue with our unit on energy and power. In the last sequence, we looked at the energy and power considerations, both static and dynamic, for our NMOS style inverters. That is our inverter built out of a MOS transistor with a resistor as the pull-up. We also showed that that kind of a structure of a circuit resulted in static power that was absolutely insane. Okay, the power was absolutely crazy. In this sequence, we will look at some really fun stuff. We will learn about a new kind of device and a new kind of inverter, which is the real way that inverters are built in industry and gates are built in industry. And these kind of gates are really the foundations of our electronic industry. Okay, you'll find hundreds of millions of these, okay, and today billions of these in your chips that are contained in your laptops and smartphones and things like that. Okay, so this will bring everything together really nicely into what is really done today. The reading for today's sequence is sections 11.4 and 11.5 of the textbook. Okay, let's get right down to it. I'm going to start with a quick review because some of the concepts here will directly relate to what we're going to cover in this sequence. So we looked at the following example circuit in the previous sequence where I had a capacitor, all right, and this capacitor was switched by two switches. Okay, there was one switch S1 and a second switch S2. We also had S1 and S2 operating such that they were never open at the same time or never closed at the same time. Okay, we looked at this example where first S1 was closed, okay, and then S2 was closed. So S1 would be closed and then S2 at the same time, S2 would be open. Okay, so that I would charge the capacitor. Then S1 would open and S2 would close in the second half of the cycle so that the capacitor would discharge through R2. Okay, and so my time period for charging and discharging was this amount of time here, okay, capital T, and that was divided into two intervals T1 and T2, where the sum of T1 and T2 was capital T, my cycle time, and which was the reciprocal of the frequency. We also saw in the last sequence that the power dissipated by a circuit such as this was given by, the average power was given by C Vs squared F, where Vs squared was the voltage to which I charged up my capacitor, okay, and then discharged that all the way down to 0. We marked this with a couple of stars, and I'm going to refer back to this formula and this kind of circuit back in a few minutes. I'm going to refer back to this formula and this same circuit in a few minutes in this sequence. Okay, we're going to show that this equivalent circuit reflects a new way of building our inverter. Notice that in the circuit, because S1 and S2 are not closed at the same time, there's never a path for the current from the voltage source through R1 and through R2 to ground at the same time. Okay, let's assume that this node is ground. Okay, so there's never a connection, direct connection between R1 and R2. Okay, and the reason is that either S1 is open, or rather either S1 is closed or S2 is closed. Both are not closed at the same time. And so therefore there is no static power dissipated, and all the power being dissipated by the circuit is dynamic power, okay, given by C V squared F. Following that circuit, we looked at our actual inverter circuit, and to the inverter circuit we connected a capacitor C at the output, and the reason we did so was to model the load that the inverter would be driving. And in this particular situation, we assumed that the input had time period T and frequency F, where my input was high for half the cycle and low for half the cycle. By doing so, the MOSFET would be switched on for half the time and then switched off for the other half of the time in each cycle. We drew the equivalent circuit for this design for our inverter circuit, and in this case notice that my power supply connects from RL through the capacitor to ground, which is Vs connecting through RL to the capacitor to ground. Let's assume this is the ground node right here. And then my VO, the node connecting RL and C, goes through R on to ground through a switch. So this node here goes through R on and passes through a switch on the way there. And that switch reflects the MOSFET. So this switch is on for half the cycle and then off for half the cycle. Okay, so this was a true representation of the MOSFET, and there's only one switch here. We showed that the average power burned by the circuit is given by this formula, where there's a static power component and a dynamic power component. Okay, the dynamic power component CV squared F was the same as the previous circuit with the double and the equation with the double star. This was my dynamic power. But in addition, because I have a direct path from Vs through RL through R on to ground when the switch is on, and the equivalent circuit, a direct path from Vs through RL through R on when the switch is on, okay, I get some static power as well. Okay, so both a static and a dynamic power. Then we looked at some numbers just to get a sense of how bad the situation was in terms of designing circuits in that manner. So we said if we assumed for our inverter, okay, if we assumed the following numbers. Okay, recall again, let me draw the inverter here very quickly for you so that you can see what the numbers are, what the numbers relate to. Again, this is C, this is RL, this is Vs, and the frequency, the input has a square wave, and with the time period t, which is equal to the reciprocal of the frequency. Vs is 5 volts. Okay, let's continue down this path and very quickly review what we did the last time. So we said the last time there was both a static and a dynamic power. This is my static power and this is my dynamic power. So let's plug in the numbers and compute what we have here. So the average power is the average power per gate is given by this expression inside the brackets, and 5 million is the number of gates that I have. So number of gates times the power per gate gives me the average power. This here is the static power, Vs squared by 2RL. That's the static power. And this is the dynamic power. This is C V squared F, where F is 3 gigahertz. The frequency. Okay, going ahead and crunching away at the numbers. The static power per gate comes out to be 1.25 milliwatts, and the dynamic power comes out to be 75 microwatts. Then if I multiply that out by the number of gates, I get a whopping 6.25 kilowatts for the static power for this chip, with merely 5 million gates, and 375 watts for the dynamic power. Now, the 6 kilowatts, which is the equivalent of about 4 to 5 irons that you would use to iron your clothes, that is a total disaster. Okay, and recall the example I used was that much power, 6 kilowatts coming out of a 1 square centimeter chip, is equivalent to the amount of power coming out of 1 square centimeter of the sun's surface. So that is a total disaster. It is a non-starter. Now, 375 watts is pretty bad. Okay, this is not something that you could have a chip and we could build a heatsink that could dissipate this amount of power. Okay, it can be done. Okay, but it requires heroics. Okay, it requires some real heroes to build those circuits and deal with it. Okay, so this is pretty bad too. But the 6 kilowatts is of course a total disaster. Okay, so we're going to start by looking at how to get rid of the static power. Okay, how to get rid of the 6 kilowatts. Okay, and once we do that, we'll then focus our attention on the remainder, which is the dynamic power.